In 1973, on the streets of Boston, people learned to look up, not out of wonder, out of fear, because the newest, tallest, most beautiful building in the city, a mirror-skinned tower 60 stories high, had started shedding its windows, not cracking them, not loosening them, dropping them. Whole panes of glass, each one 4 feet by 11 feet, each one weighing 500 pounds, tearing loose from high up the face of the building and falling hundreds of feet to the pavement below. Whenever the wind rose past 45 miles an hour, the police closed the streets around the tower. At one point, an entire acre of the building's face, more than 60 of its windows, had been replaced with sheets of plywood so that from a distance the proud glass skyscraper looked like it was wearing bandages. People called it the Plywood Palace. That building was the John Hancock Tower, and it was in the middle of becoming the most famous engineering embarrassment in America. But hidden inside its troubles was a second problem, quieter and stranger than the falling glass. A problem that would force engineers to confront something deeply counterintuitive about how tall buildings survive. Because the tower had another flaw, it swayed, and the people at the top were getting seasick. Tonight we're going to work out something that sounds, at first, completely backwards. That the tallest buildings in the world are not designed to stand rigid against the wind, they are designed to move with it. That a skyscraper which refused to bend would be far more dangerous than one that sways, and that inside some of the most famous towers on Earth, engineers have deliberately installed enormous weights, hundreds of tons of steel and lead, whose only job is to let the building move correctly. To understand why, you have to start by throwing away your instinct about what strong means. When you picture a strong building, you picture something solid, immovable, a structure that plants itself against a storm and does not budge an inch. That is what strength looks like to us. Resistance, stiffness, refusing to give way. For a very tall building, that picture is not just wrong, it is deadly. Here's the problem. A skyscraper is not really fighting gravity. Gravity pulls straight down, and columns handle that easily. Stacking weight is the easy part. The real enemy of a tall building comes from the side, wind, and the taller you build, the worse it gets, because wind is stronger, higher up, and because a tall building is essentially a long lever. A force pushing near the top of a 1,000-foot tower has enormous leverage trying to bend it over. Now imagine you tried to beat that force with pure stiffness. Imagine you built a tower so rigid it would not move at all. What happens when the wind hits it? All of that force has to go somewhere. In a rigid structure, the energy of the wind cannot be absorbed by movement, so it concentrates. It piles up at specific points in the frame, the joints and connections where the stress has nowhere to escape, and materials that are loaded hard at a single concentrated point do not bend gracefully. They fail suddenly. They crack. They snap. The stiffer you make the building, the more brutally the force lands, and the more likely it is to break something all at once, without warning. A flexible building does the opposite. When the wind pushes, the building leans, just slightly, and that movement spreads the force out across the whole structure instead of dumping it on a few joints. The steel frame flexes, absorbs the energy, and springs back. The building bends so that it does not break. It survives the storm not by defeating the wind, but by going along with it a little, in a controlled and predictable way. This is the core idea, and it is worth saying plainly because it runs against everything our gut tells us. For a skyscraper, strength is not the ability to stay still. Strength is the ability to move and to recover. A tall building shows its strength through controlled, predictable, recoverable movement, not through rigid resistance. Rigidity is the enemy, so engineers build tall towers to sway. And they do sway, far more than most people realize. At the top of a super-tall skyscraper, in a strong wind, the building can lean and swing through a distance measured not in inches but in feet, moving back and forth on a slow rhythm that takes several seconds to complete each cycle, which brings us straight to the next problem, and back to the seasick occupants of the John Hancock Tower. Because there is a catch. The building can tolerate this movement just fine. The steel does not mind swaying. That is what it is designed to do. But the people inside mind very much. Human beings are astonishingly sensitive to motion. You do not need to be thrown around to feel unwell. It turns out people can detect accelerations as small as 0.05% of gravity, a movement so gentle you could not see it, but your inner ear can feel it. And on the upper floors of a swaying tower, where the movement is greatest, that gentle, endless, slow rocking is enough to make people genuinely, miserably seasick. Nausea, dizziness, that queasy sense that the floor is not where it should be. So now engineers are caught between two truths that pull in opposite directions. The building must be flexible enough to survive the wind without breaking, but it must not move so much that the people inside cannot bear to be there. You cannot solve this by making the building stiffer. That brings back the danger of sudden failure. You need something else. You need a way to let the structure flex while quietly canceling out the worst of the motion the occupants feel. And the solution engineers landed on is one of the most elegant and strange devices in all of structural engineering. They fight the building's movement by adding, of all things, a giant weight that moves too. It is called a tuned mass damper. Here is the idea. Somewhere near the top of the tower, you install an enormous mass, hundreds of tons of steel or lead, sometimes hung like a pendulum, sometimes sitting on a slick, lubricated surface so it can slide. This mass is connected to the building through springs and shock absorbers, and it is carefully tuned so that its natural rhythm of swinging matches the building's own natural rhythm of swaying. Now watch what happens when the wind pushes the tower one way. The building starts to lean, but the giant weight, because of its inertia, does not want to move. It lags behind, staying roughly where it was. So as the building swings to the right, the mass is effectively pulling to the left, dragging against the motion. It is always a step behind the building, always pulling the opposite way, always fighting the sway, and the shock absorbers turn that fight into heat, bleeding the energy of the movement away. The building still flexes. It still has the safe, necessary give that keeps it from snapping. But the wild, stomach-turning swing at the top is tamed, quietly counterbalanced by a slab of metal moving in opposition to it, second by second, for as long as the wind blows. In the John Hancock Tower, the fix was two enormous weights, 300 tons each, installed high in the building. They sit on a thin film of oil so they can slide, tied to the steel frame with springs and dampers, and as the tower sways, they slide the other way and haul it back. That single system turned the seasick tower into what is today considered one of the safest skyscrapers ever built. And once you know what to look for, you find these hidden weights inside the most famous towers on Earth. The most spectacular of them all is in Taipei, in the skyscraper called Taipei 101. For years, the tallest building in the world, standing in a place regularly battered by typhoons and rattled by earthquakes. If any building on Earth needs to move correctly, it is this one. And Taipei 101 does something almost theatrical about it. Instead of hiding its damper away, it puts it on display. Suspended in the heart of the tower, hanging through several floors near the top, is a gigantic golden sphere, a steel pendulum weighing over 700 tons. Visitors can walk right up to it and watch it. When a typhoon hits the city, that enormous golden ball swings visibly against the building's motion, drifting one way as the tower leans the other, holding the skyscraper steady from the inside. In a strong enough wind, the tower itself can move well over half a meter near the top in a matter of seconds, and the pendulum is what keeps that movement from ever becoming unbearable or dangerous. It is one of the few places in the world where you can stand inside a super tall building during a storm and actually see the thing that is saving you, swinging slowly overhead. And Taipei 101 was not the first tower to trust its safety to one of these weights. One of the earliest and most dramatic stories belongs to a skyscraper in New York, the Citicorp Center, finished in the late 1970s. It was a striking building, lifted up on massive columns, placed not at its corners but in the middle of each side, an unusual design that made the tower especially sensitive to wind coming at its corners. To keep it comfortable, the engineers gave it one of the first tuned mass dampers ever built into a skyscraper. A 400-ton block of concrete near the top, floating on a film of oil, sliding to counter the sway. But the Citicorp Center hides a far more unsettling story, and it is one of the most famous near misses in engineering history. After the tower was already finished and occupied, its own structural engineer received a question from a student that made him recheck his calculations. When he did, he realized something horrifying because of a change made during construction. Bolted joints used instead of welded ones. The building was far weaker against those corner winds than anyone had thought. By his estimates, a powerful enough storm, the kind that might strike New York roughly once in a human lifetime, could potentially knock the tower down. What followed was extraordinary. Through the autumn during hurricane season, crews worked in secret at night after the offices emptied, welding steel plates over the building's weak joints to reinforce them, while most of the public never knew there was a problem at all. And the tuned mass damper, the great sliding block near the top, was part of what bought them time. As long as it kept working to reduce the sway, it lowered the forces on the frame while the repairs were carried out. A device installed merely for comfort turned out to be helping hold the building together during the weeks it took to fix. It is the clearest possible illustration of how seriously engineers take the movement of tall buildings, and how thin the line can be between a tower that stands and one that does not. So the picture is complete. The building is built to sway because a rigid tower would break. The sway is then tamed, not by fighting the flexibility, but by adding a huge counterweight that moves in opposition. Flexibility keeps the building alive. The damper keeps the people comfortable. Two ideas that both depend on movement, working together in a structure we naively think of as perfectly still. But I want to go back, one more time, to the John Hancock Tower, because its story carries a warning that engineers have never forgotten. Before that, though, it is worth asking a simple question. How does anyone know, before a single floor is built, exactly how much a skyscraper is going to sway? You cannot guess. Guessing wrong means either a dangerous building or a seasick one. The answer is that long before the tower exists, a small version of it already does, in a wind tunnel. Engineers build a scale model of the proposed skyscraper, sometimes along with models of all the surrounding buildings, because the wind in a city does not flow cleanly. It is funneled, twisted, and sped up by every neighboring tower. They place this model in a wind tunnel packed with sensors and blast it with carefully controlled airflow, measuring exactly how the model bends, twists, and vibrates. They can find the building's natural rhythm of swaying, spot the wind directions that trouble it most, and discover nasty surprises like a tendency to twist as well as lean, or to catch the wind in a way that makes the sway build up rather than die down. Only once they know how the finished tower will move can they decide what it needs, how flexible to make the frame, whether it needs a tuned mass damper, and how heavy that damper has to be. The giant weights near the top of these buildings are not guesses. They are precisely sized answers to a question that was asked years earlier of a model no taller than a person in a room full of artificial wind. Now, back to the John Hancock, because its story carries a warning that engineers have never forgotten. Remember, the Hancock had two separate problems, and it is important not to confuse them. One was the sway solved by the tuned mass dampers, but the other, the falling windows, was something else entirely, and in some ways more frightening, because it showed how a tiny, invisible detail can bring down a giant. The windows were not falling because the building swayed too much. After enormous amounts of testing, engineers traced the failure to the windows themselves, specifically to the thin layer of air sealed between the two panes of glass in each window unit, bonded to a reflective coating. That seemingly minor design choice was causing the glass to fail and tear loose. The solution, in the end, was almost humble. Every single one of the building's more than 10,000 windows was replaced with a single sheet of tempered glass. Think about the gap between the two problems. One was grand and dramatic, a skyscraper swaying in the wind, tamed by 300-ton weights. The other was almost microscopic, a thin pocket of air inside a pane of glass. And yet it was the small, hidden, unglamorous flaw that had police closing streets and dropping 500-pound windows onto the sidewalks of Boston. The engineering that keeps a tower standing is not only in the huge, visible systems, it is in the tiny details that no one on the street will ever see. That is really the lesson buried inside all of this. We look at a skyscraper and we see something that appears completely, reassuringly still, a fixed thing, planted in the ground, unmoving. But that stillness is an illusion, and a carefully engineered one. The building is not still. It is swaying, gently, all the time. Deep inside it, a mass of metal may be sliding back and forth to hold it steady. Its frame is flexing with every gust, spreading the load, bending so that it will never have to break. The strength of a great tower is not that it refuses to move. It is that it moves exactly as much as it should, and no more. So the next time you stand at the foot of one of these buildings and look up, remember what you are actually looking at. Not a rigid monument fighting the sky, a structure in constant, invisible motion, designed by people who understood a truth that still feels wrong in the gut. That the safest way to stand against the wind is not to resist it, but to bend. The building sways because it is strong, not in spite of it.